Welcome to The Explainer. Today, we are getting into one of the most incredible, most fundamental processes in the entire universe. We're going to break down the cosmic recipe for how a star is actually born, from what starts as a cold, dark cloud into a brilliant furnace of light. So, what does it take to cook up a star? I mean, you might be imagining some huge cosmic explosion, right? But the truth is, it all starts not with a bang, but in the quietest, the coldest, and the absolute darkest corners of space. Okay, so our very first ingredient is what we call a stellar nursery. These are just these enormous dark clouds of gas and dust, and they're just floating around in the space between stars. This is where all the magic begins. You know, that space between the stars, it isn't really empty. It's actually filled with what astronomers call the interstellar medium. Think of it like a really, really thin cosmic soup of gas and dust, and it's made of mostly hydrogen and helium. I mean, the most basic building blocks of the universe, with just a tiny sprinkle of heavier stuff mixed in.
But here's the thing. These stellar nurseries, they're incredibly shy. They are so full of these tiny, tiny particles of interstellar dust. Each one is smaller than a micrometer, that it all acts like a thick cosmic fog. It completely blocks out visible light, hiding all the action, all that star formation happening deep inside.
So how do we peek inside? Well, we have a trick up our sleeve. We switch our vision. While regular light gets stopped dead in its tracks by that dust, longer wavelength infrared light, it can pass right through. It's kind of like having cosmic X-ray vision. It lets us peer right through that dusty curtain and see all the newborn stars glowing away inside. All right, so we've got our giant cloud of raw materials. But how does a big, spread-out cloud turn into a dense, hot star? Well, it all comes down to a massive cosmic tug-of-war. What you've got here is this epic battle between two fundamental forces. On one side, there's gravity, and it is relentlessly trying to squeeze the cloud, pulling all of that gas and dust inward. And on the other side, you've got thermal pressure. That's just the heat from all the little gas particles bouncing around, pushing outward, trying to make the cloud expand. Now, for a star to actually form, gravity has to win this fight. And it wins by being smart. See, these giant clouds, they aren't smooth. They're messy, they're turbulent, they're lumpy. And gravity can focus all its effort on the densest lumps, where its pull is the strongest. It's in these little pockets that gravity finally overwhelms the pressure. And that lump begins to collapse on its way to becoming a brand new star, or maybe even a whole cluster of them. Okay, let's zoom in a bit. Let's follow just one of these collapsing lumps as it goes through this incredible transformation, from a cold piece of a cloud into a glowing protostar, a real star in the making. So, as our little cloud fragment gets smaller and smaller under the pull of gravity, something amazing happens. It starts to spin. Faster and faster and faster. This is all because of a fundamental law of physics you've probably heard of, the conservation of angular momentum. All that slow initial rotation of the huge cloud gets concentrated as it shrinks. And this is something you've actually seen before. It's the exact same reason an Olympic ice skater spins so much faster when they pull their arms in close to their body. The collapsing cloud is doing the very same thing, just on a cosmic scale. Now, this rapid spinning is a huge deal. It causes the particles to collide and flatten all that infalling material into a rotating disk that forms around this central growing protostar. And this disk, this is critical. It's the birthplace of future planets. And at the same time, this whole system can launch these incredibly powerful jets of gas that shoot out from the North and South poles at unbelievable speeds. So our protostar is really taking shape now, right there in the center of this swirling disk. It's hot, yeah, and it's definitely glowing, but it's not a true star just yet. The final, most critical step in this whole recipe is just about to happen. And this is a really important thing to remember. Up until this point, all the light and heat that we're seeing from the protostar is just from the energy of the collapse. It's basically cosmic friction. The core itself is still not hot enough to kick off the main event. So, what's the magic number? Well, it all comes down to temperature. Gravity just keeps squeezing and squeezing and squeezing that core, and the temperature keeps rising. When it finally hits about 10 million Kelvin, the conditions become so hot, so dense, that nuclear fusion ignites. And at that exact moment, a star is born. The new outward pressure from that fusion engine in the core perfectly balances the inward crush of gravity, and the star becomes stable. For a star just like our sun, this entire journey, from a cold bit of a cloud to a stable, shining star, took about 30 million years. So we've made our star, it's shining bright. But that brings up a really interesting question, doesn't it? Are there limits? Can a star be any size it wants, or are there some cosmic rules about how big or small they can get?
Oh, you better believe there are limits. On the small side, if a collapsing cloud fragment has less than about 8% of the sun's mass, a weird quantum force called degeneracy pressure stops the collapse before the core ever gets hot enough for fusion. What you get is a failed star, what we call a brown dwarf. And on the other end of the scale, if a star gets to be more than about 150 times the sun's mass, it becomes so incredibly bright that the pressure from its own light literally blows its outer layers right off into space.
And if you were to say, take a census of all the newborn stars out there, you'd see the universe has a very clear preference. For every single massive star it makes, it churns out tons and tons of smaller, low-mass stars, kind of like our sun. The little guys are, by far, the most common type of star in the entire cosmos. And that leaves us with this final, really fascinating thought. If the universe is just absolutely packed with these common, super long-lived, low-mass stars, then why is it that we owe our very existence, all the heavy elements in our bodies on our planet, to that tiny, tiny fraction of rare, brilliant, massive giant stars? Well, that's a story for another explainer.